Welcome to the second video on the example problem for unsymmetric bending. In this video, we'll go through finding the angle of the neutral axis and the angle of the moments that are applied to this cross-section. Now that we've determined the second moment of inertia for both of the directions of this cross-section, it's time to find the angle of the total moment. So there's two ways to think about this. One is to think about the direction of the moments themselves. That is to say, about the axis. So in this case, we have 15 kip inches in the z direction, which we said was this direction, and 10 kip inches in about the y direction. So when we're doing this, we're going to think of the right-hand rule, and so we're going to say that for the z direction and that for the y direction. So if we want to determine the total direction, we're just going to need to draw it up like this. And we've got 15 in the z direction, and we've got $10 in the y direction, which is going to give us a resultant in this direction. And this is 15 right here, like I said, 15 kip inches. This direction right here, this angle, theta, will tell us how much we rotated. So in that case, what I would recommend doing, really there is only one way to proceed from here, right? We need to use a trigonometric function, so we can say that the tangent of this theta is equal to 10 kip inches divided by 15 kip inches. I think you can recognize that right there. And then popping an arctangent into both of them will give us that this angle is equal to 33.69 degrees. So our new direction is going to be 33.7 degrees from that, and we're going to be rotating like that. So that was terrible for video, but we're going to be rotating in that way in this direction. And this is probably the more common way to do this. The book also appears to do something else, where it talks about the plane in which the moment is acting. Now, most of you were in my class last semester, and even if you weren't, you've certainly been through moments and cross products before. So if we have moment in the z direction, you're going to presumably at this point know that it's a result of action in the x direction and the y direction. So that's the plane that's going to be acting. If we looked at the round circle, the wheel that we would draw for that moment, it would be in the x and y plane, and it wouldn't move, or it wouldn't take up any dimension in the z direction. Similarly, for moment about the y-axis, it would be acting in the z-plane and in the x-plane, but it would not be acting in the y direction, its moment about the y-axis. If you want to think of it that way, that's absolutely fine, but you do need to switch from thinking about it being in the x direction, the typical direction for a moment, and instead think of it as being in the y direction, because if we have moment about the z-axis, which is going to be the most typical that we're going to think about, in that case, then it would be acting in the xy plane, not in the z plane. So if we do that, we're going to say that, well, in this case, that's going to be down, because if we look at the right-hand rule, our z direction is going to be, there's positive z, that's forward, so it'll be down 15, oh, I forgot to color code it, and it will be left, or right, yeah, I'm not good at those, it will be right 10, and that's going to give us the exact same answer that we got when we thought about it in terms of the axis. We're still going to be using the tangent. That right there is 10. That's 15. But now, instead of looking at our angle against the x-axis, we're going to be looking at our angle against the y-axis. So I think you can go ahead and tell that's just the same triangle. We're thinking about it different ways, but we're going to get the same value of 33.7 degrees. So that's the direction, that's the angle for the moment, but it is not the angle for the neutral axis. For the neutral axis, we'll have to use another equation. So let's do that. Now that we have the angle that the moment is acting at, 33.7, we can find the angle that the neutral axis is at. So that's going to be an application of this equation. The tangent of the angle that the neutral axis is at is going to be equal to, well, y over z, or the second moment of inertia about the z-axis divided by the second moment of inertia about the y-axis times the tangent of the angle that the moment is at. So we can determine that it is the arctangent of 1.0833, that's repeating, inches to the fourth divided by 3.0833, repeating, inches to the fourth times the tangent of the angle 33.69 degrees. Sorry. There we go. Let's not overdo that. Which will give us 13.18 degrees. So that's the angle that our neutral axis will be at, much smaller.